Check. Okay, so maybe let's continue. So, but before we resume, like a couple of things. So one, I checked the Piazza question about the cross-validation thing. Well, I think TAs have said it is okay. Just to be consistent, we will consider both both types of solutions. Like one where you're doing cross-validation with just the training set. And first of all, to do grid search, you don't need to do cross-validation. Like you can just train with the training set and do model selection with validation set. So there is nothing in grid search which is linking you to do cross-validation, like K4 cross-validation. Okay, so personally, I think you should not combine the training and validation set because they are given to you for a purpose, but to be consistent with the answer in Kaggle, like so in Piazza, we are going to accept both types of solutions. So, but if you want to change your mind, you still have time to just not do this combination of training and validation. But we are not going to penalize for that. Okay, so that is one, and there's a chat about looking for a third teammate. So I know that you're towards the end of signing up, and there are still some pairs of two who are finding it very hard to find a third teammate. Now, I think the solution will not resolve unless people like three teams of two combine to form two teams of three. Okay, but I understand that it is very difficult to do that without seeing people in person. So there is a recommendation about using the Discord for the Slack, like for the course. I'm not in the Discord, but I think all of you are. So like if you want to find teammates, you can find that in Discord or maybe in Piazza. It might be a useful idea to start a thread in Piazza with all the two-member teams currently looking for three-member team, because I think the only solution is when you really merge 3 teams to 2 teams. Okay, because maybe there are 5 of you or 6 of you, 2 teams, like who are looking for the third person, and there is no third person free in the class because everyone is paired up already. So try to do that. In the extreme case, like if you don't find anybody before the deadline, like you can register as a team of 2. Okay, so but maybe we will shuffle you tomorrow, like if we find there are too many teams of 2. Okay, so we will think about it tomorrow, but for now, do your best to find the teammates. Okay, so let us continue. So before the break, we decompose the error function because we are doing the sequential minimization, right? Like so, we assumed we have alphas and y's for up to m-1 classifiers, and we are doing that for the mth classifier. Now, for the mth classifier, we derived that the best way to find the parameters of the classifier is by minimizing this error function, right? Now, how do I find the alpha m? Okay, to do that, we're going to take this particular error function. Okay, copy. Okay, so we're going to take this particular error function and we are going to do dou E by dou alpha m. So can somebody tell me what are all the terms which has alpha m? So what are all the terms which has alpha m? All the terms, right? So like there are 2 terms here. The first term is this, so that has alpha m in it. The second term is this, that has alpha m in it. So, but this is an easy differentiation because e power alpha m is just e power alpha m, right? So we just need to take care of the plus or minus there. Okay, So now we are going to do the differentiation. So there is going to be 1 over 2 coming all the places because it is e power alpha m by 2. So I'm going to take the 1 over 2 completely outside. Then you have e power alpha m by 2. When you differentiate that, you just get e power alpha m by 2 multiplied by 1 over 2. That 1 over 2 is outside. Then you have minus e power minus alpha m by 2. When you differentiate this, you get a minus 1 by 2 coming out. So this becomes plus. Okay. The whole thing multiplied by summation n is equal to 1 to capital N Wn of m, indicator function of ym of xn not equal to t of n. Okay. Then you have the second term. So here you have plus e power minus alpha m by 2 summation over n is equal to 1 to capital N Wn of m. However, when you differentiate minus alpha m by 2, you get a minus. So I just need to remove this plus and put a minus here. Is that clear? This whole thing is equal to 0. So half doesn't matter because it goes to 0. And all you have is these two terms. I'm going to rearrange them. So summation n is equal to 1 to capital N Wn of m indicator. Just to make my writing easier, I'm going to put indicator like this. Okay. So, but you know that the indicator is for wrong examples. Okay. Indicator divided by summation over n Wn of m is equal to e power minus alpha m by 2 divided by e power alpha m by 2 plus e power minus alpha m by 2. I skipped a bunch of steps here. Like, so you put the second term to the right hand side, then you rearrange things, you get this. Is that clear? Okay. Now, we have seen this term before. What is this? What?
Function to be minimized.
Sorry, what?
Function to be minimized.
No, that is not this function. Yeah. It's the epsilon, right? Like, if you remember the Adabos algorithm, we computed epsilons and alphas. Epsilon was the weighted error rate, right? Like, so that is this epsilon. This is epsilon m. So epsilon m is equal to e power minus alpha m by 2. Okay, so maybe instead of doing the whole thing, I will just differentiate numerator and denominator by e power minus alpha m by 2. So this becomes 1 by 1 plus e power alpha m. Okay. Now we are looking for alpha m, right? So 1 plus e power alpha m is equal to 1 over epsilon m. E power alpha m is equal to 1 minus epsilon m by epsilon m. Okay. And finally, alpha m is equal to ln 1 minus epsilon m divided by epsilon m. Is that clear? So this is exactly what Adabos is doing, right? Like, so we have derived Adabos from scratch now. Like, so like we started with the exponential error function. If I want to minimize this exponential error function in a sequential way, one after the another, like, then this is what my alpha m is going to be. And at each step, I'll be minimizing the weighted error with respect to the classifier and then compute epsilon and alpha. Then you're done, move to the next, move to the next. Is that clear? Any questions? Okay. Now, how do I update the W's, right? So Wn of m plus 1, the weight for the new classifier is given by Wn of m multiplied by x of minus 1 over 2 p of n alpha m ym of x of n. Okay. This is coming from the previous equation that we had for Wm. Okay. So now we are going to use this identity that T of n multiplied by ym of x of n is equal to 1 minus 2 times indicator function of ym of x of n not equal to T of n. Okay. So this identity is easy to verify. So when it is a wrong example, T of n multiplied by y of m is equal to be 1. Sorry, it's going to be, when there is a misclassification, then this is going to be 1 minus 2, so minus 1. When it is correctly classified, then you have 1 minus 0, so plus 1. Okay, this is just a compact way of writing both. Now, I can substitute this in the previous equation, okay, so which will give me Wn of m plus 1 is equal to Wn of m, okay, exp of minus alpha m by 2, okay, exp of alpha m indicator function of ym of x of m not equal to y of p of m. Okay, so here you see that this particular thing is independent of n, so I can just very well remove this. Okay, because that is going to be added to all the examples. I can just very well remove this. Then you have this remaining thing, which is exactly what we are doing in boosting, right? So is that clear? Any question about add a boost? Okay. Now that's the end of add a boost, but we have seen this new error function, right? Like exponential error function. Now let's try to understand what is the best. Somebody asked this question. So what is the best that we can do with exponential error function? Okay. So for example, we know that if you have a least square error function, then the best we can do is conditional mean, right? Like so, like you can do whatever type of classifier you want, but the optimal thing that you can do is just a conditional mean, right? Like so if you are using least squares. Similarly, what is the optimal thing that one could achieve? Like if you're using exponential error function, okay? Now, this is very simple. Like we're just going to compute the expected error, differentiate it to 0. That is my answer, right? So now the expected error is given by expectation with respect to x comma t, x of minus t y of x, right? So this is nothing but summation over t, integral over x, okay, because t is discrete, x could be continuous, x of minus t y of x multiplied by p of t given x, p of x dx. Okay. Now I need to differentiate this with respect to y of x and set it to 0. That is my optimal y of x, right? So now dou by dou y of x of this whole thing, right, is given by minus summation over t, okay, t times x of minus t y of x, probability of t given x, p of x. I'm differentiating an integral, okay, so this is what I would get. Now that's because like we have e power minus tx. When you differentiate e power minus tx, you get e power minus tx and minus t also, so minus t comes outside. Okay, now I can actually expand this. So what happens if t is equal to 1? What happens if t is equal to minus 1? So this is basically x of y of x, okay, p of t is equal to minus 1 given x minus x of minus y of x when p is with probability of t is equal to 1 given x multiplied by p of x. Is that clear? When t is equal to 1, this becomes e power minus y of x. When t is equal to minus 1, this becomes e power y of x. Right? Now I'm just going to setting this equal to 0. So that gives me x of y of x, probability of t is equal to minus 1 given x, okay, is equal to x of minus y of x, probability of t is equal to plus 1 given x. Now I'm going to rearrange. So this becomes x of 2 times y of x is equal to probability that t is equal to minus 1 given x divided by probability, sorry, is equal to plus 1, t is equal to minus 1 given x. Okay. Or in other words, y of x is given by 1 over 2 ln probability that t is equal to 1 given x divided by probability that t is equal to minus 1 given x. Okay. Now we have seen this term before, right? Like, so when we talked about two-class classification, this is the log odds ratio, right? Like, so this is the log of the ratio of probability being 1, the class being 1 and class being minus. So what exponential error is trying to do is to find this log odds classifier. Okay, so it is seeking the best approximation to this log odds ratio. Okay, but however with some constraint. The constraint being that we are doing some linear combination of bunch of classifiers which are each trained in a sequential way. Is that clear? Now, how would this exponential error function look like? So here you can see all the error functions that we have seen so far. Okay, but I removed exponential, like I removed least squares because it's a bad error function for classification, right? So here you can see the 0-1 loss, the usual 0-1 loss, right? Which is the step function. So then you see the red line, which is the cross entropy, right? And then you see the blue line, which is the hinge loss, hinge, okay? And the green line that you're seeing is the exponential error function. Okay, so now you can see how strong is this exponential error function. Like, so both your hinge loss gives linear error, right? And cross entropy loss gives almost linear error. It's non-linear, but it is almost linear. However, exponential error loss gives you like exponential error when you make mistakes. So it tries to reduce the mistakes as quickly as possible. Okay, so which is also one of the reasons why this boosting technique works very well. Is that clear? Any questions? Okay, so now I just want to quickly talk about bagging again. So bagging versus boosting. Okay, now these are two different methods, right? Like, so bagging is this idea of combining many things in parallel. Boosting is this idea of combining many things in sequential order. So as you can imagine, bagging is going to be faster because you can train all of them individually. Like if you want to train to 10 classifiers, train them individually. But boosting is going to be slower. Okay. However, bagging gives you small error reduction. By bagging a bunch of things, you can get like 1%, 2% improvement. So that last 1% that you want to win the competition, right? But boosting is not like that. So boosting could actually give huge error reduction, like if you do it well. Okay. Now, for doing bagging, it needs reasonable classifiers. So works well with reasonable classifiers. You cannot bag bad classifiers or like not very good classifiers. Okay. However, boosting actually works even with simple classifiers. Okay. These are all good things about boosting. Well, first thing is negative, like the other two are positive, right? There's another negative thing about boosting, which is like bagging is not that susceptible to mislabeling. Okay. However, boosting can overfit to mislabels. Is that clear? And finally, the whole idea of bagging is to reduce variance. Right? Can somebody tell me what boosting is trying to do? Is it trying to reduce variance or bias? What is boosting trying to do? So the base classifiers that we use in boosting, right? Like, so do they have high bias or high variance? Yeah.
Well, bias is the error of the model, so it tries to reduce bias. Because the idea is that we work with the same data, but we try to focus the model on the errors that made on this duration.
Yeah. So intuitively, boosting focuses on the bias, right? So that is also another reason why you can afford to use simple classifiers. Like the decision stump classifier that we have seen is the most biased model, right? Like, so it is not even as powerful as a linear classifier. Like it's just one feature, right? So you can take extremely biased classifiers and reduce their bias by doing boosting. Okay, so boosting reduces biases of extremely weak high bias classifiers. Okay, so these are two different techniques. Like so, bagging takes a bunch of low bias high variance models and reduce the variance. On the other hand, boosting takes a bunch of high bias models and reduce their bias. Is that clear? They are already low variance models, right? Like so, there's not a lot of variance with a decision stump. So this is trying to reduce the bias. Okay, so okay, there are many answers in the chat which are all correct. Good. Okay, I think that concludes our discussion on ensemble methods. Okay, so for your competition, I highly encourage you to try these ensemble methods. Like so, it is as easy as trying an SVM or logistic regression in your sklearn. So, but there are also a lot of other packages available to do these kind of things. Like boosting has its own package, which is very famous, and it has a lot of advanced boosting algorithms implemented. Okay, so I recommend you to explore all these things while trying for your competition. Yeah.
In the kind of competition, all libraries related to machine learning are permitted.
Sorry, what?
That means we can use sklearn, PyTorch, we can use anything.
You can use whatever package you want, but remember, you cannot use a pre-trained model. Like for example, if you use Keras and download a convolutional network which was already trained, that is not allowed.
I don't understand it. What do you mean? So like,
you can use whatever package you want, but the weights of the model or the parameters of the model has to be learned from scratch. You cannot use parameters from packages. Is that clear? Okay. Yeah.
I don't think for the final exam,
Hmm?
in the 3 hours that you consider, is there the exam is made for 3 hours, or is the exam made for less time considering the time of scanning and sending our PDF?
Well, I will definitely give time for scanning and sending the PDF, but I haven't decided whether it is going to be 2+1 or 3+1.
Okay.
It is, but there will be time for scanning your PDF and sending it. Okay, so I think that concludes our discussion on ensemble methods. Okay, so now we are going to move to a fresh topic, even though I try to do one topic per week. Sometimes we have to move like this. Okay, so now we are going to talk about like probably our second completely nonlinear method. Like so we have seen nearest neighbors before, right? Like so we're going to talk about neural networks, okay, which are currently the most successful class of machine learning algorithms. Okay, so I say currently because we don't know what's there in the future. So for now, like neural networks are everywhere in machine learning. Okay, so even though this is not a course on neural networks, like we will try to give a good introduction to neural networks. And if you want to learn more about neural networks, so there is a course on deep learning at UDM taught by Aaron Colville next semester. So I highly encourage it as a follow-up for this course if you want to learn more about neural networks. Also, it is one of the most famous courses that gets filled very quickly. Probably they run out of seats now. So if you're interested in neural networks, like I encourage you to go sign up as soon as possible through the inter-university registration system. Okay, so now let's start. So to start with neural networks, okay, so we are going to go back in our course structure, and we are going to talk about perceptrons once again. Okay, now if you remember perceptrons, it's a very simple model, right? Like so, which is going to have a threshold to decide whether it is a positive class or negative class, right? Now, I also told you that perceptrons were introduced in, I think, 1952. And when perceptron was introduced, it was one of the earliest machine learning algorithms. And the media went crazy. Like they thought that is the most complex machine learning algorithm one can invent. And people are starting to make a lot of claims that they can do this with perceptron, that with perceptron. Okay. So, however, in 1969, so two researchers, Minsky and Papert, okay, showed a very simple example, which they also proved that perceptron cannot solve. Okay. The simple example that they showed is the problem of Xor problem. Okay. So, like if you have done a digital circuits course, you know what is an Xor function, right? Even if you have done a logic course, even if you have not done a logic or digital circuit course, like here is what the Xor problem is. Okay, so you have X1 and X2, two input features. Okay, my output is the Xor. So my output is going to be 1 only when one of the two features is 1. It is exclusive OR. Okay, so if it is 0, 0, the output is 0. 0, 1, so exclusively one of them is 1, so output is 1. 1, 0, output is 1. 1, 1, output is 0. Okay. Now, if I have to compare this with the usual OR function will have the final entry 1, 1 also to be 1. Okay. Well, this is my XOR function. Now, let us look at how this. There are only 4 examples in this data set. So let us plot these data sets in the data space and see how it looks like, right? Like so, I have 2 features here, X1 and X2. Right? And there are only 2 possibilities, 0, 1, 0, 1. When it is 0, 0, answer is 0. 0, 1, answer is 1. 0, 1, answer is 1. 1, answer is 0. Right? Now I want to design a classifier which will classify zeros and 1. First question, can I use Perceptron to solve this problem? Okay, there is some answer in the chat, but why is the class silent? So can I use Perceptron to solve this problem? Yeah? Yes, so you cannot because Perceptron is a linear classifier. Can I use logistic regression to solve this problem? Okay, so there are answers in the chat, but what about the class? Yeah?
If you use the correct yeah, but otherwise.
Okay, so if you use correct basis functions, yes, otherwise you cannot because logistic regression is also a linear classifier, right? So now to correctly solve this problem, you need a classification, the function, decision function that looks like this, right? Like anything within the ellipse is 1, outside is 0. However, if you use Perceptron, you cannot solve this problem simply, right? Like this was not very clear in 1960s. Okay, now it is clear for us because we know that this is not a linearly severable problem and Perceptron is a linear classifier, so we cannot do that. But it was not very clear at that time. Okay, so people were thinking that if you cannot solve such a simple problem with Perceptron, then probably you cannot solve any real life problem with Perceptron, right? So there was this big negative image on this line of Perceptron style algorithms, okay, which was introduced by this book on perceptrons written by Minsky and Papert, okay. So they basically wrote a book to kill the field. But that was not their intention. Okay, so their intention was to show the limitations so that people can work on the limitations. But researchers then actually took it in a wrong way. They thought, okay, this is a hopeless direction, so we should not work on this. Okay, for the next 20 years, nobody wanted to spend their time on solving this issue. Like, how can I fix the perceptron to learn a nonlinear like decision function? Okay, but now we have all the tools, right? Like we have learned about basis functions. We know that if you construct good nonlinear basis functions, then you can actually solve this problem, right? Like so, here is such a simple nonlinear basis function. Okay, so the basis function I'm going to use are like I'm going to use 2 basis functions. My first basis function is AND of x1 x2 bar. Okay, And the second basis function is AND of x1 bar x2. Out of curiosity, how many of you have done basic logic or digital circuit courses before that you know what is AND or XOR? At least a majority. Okay. So okay, for people who have not done these kind of Boolean logics, just take this as some random example. Okay, but for others, you know what is an AND function. But for people who have not done this, like so, AND function is going to be 1 whenever both are going to be 1. And I have x2 bar here, which means I'm going to take the negation of x2. So if x2 is 0, I'll take 1. If x2 is 1, I will take 0. Okay. Now I use these two basis functions. Okay. This is my first basis function. Let's call it phi1. So phi1 is going to be AND of x1 bar x2. And my phi2 is going to be AND of x1 x2 bar. Okay. Now an interesting thing happens. So with this basis function, right? Like so, both the zeros get collapsed. Okay, and the ones stay in the same place. So by doing this basis function transformation, I converted a not linearly separable problem to a linearly separable problem, right? So now I can use my perceptron on the top of this. Like I can draw a line here. Sorry, I can draw a line like this, which separates zeros and ones, right? So the problem is solved. Now, what is basis function doing here? Anybody? So what is the role of basis function? We did talk about this towards the end of one of the lectures, yeah?
Like it changes the data set.
Yeah, it does some transformation to my data so that the problem becomes easier to solve, right? Now, the most important part of this whole process is somehow I came up with these two basis functions, and x1 x2 bar and x1 bar x2, right? How did I come up with these basis functions, right? Like so, probably the person who initially came up with these basis functions tried all possible combinations of AND, OR, XOR, NOR, XNOR, right? Like so on, like basically you do all sort of engineering that you want to do with these basis functions until you figure out a basis function which makes the problem easier, right? Now, this process might have worked for this XOR problem. It will definitely not work for more complex problems, right? Like imagine you have 1,000 features, which is not even million features. It's just 1,000 features and let's say 100 examples. How would you construct basis functions with a guarantee that it is going to make the problem simpler, right? So it is not very clear, right? So in some sense, it would be nice if we can have an oracle which tells us, hey, for this problem, this is the basis function that you should use. Okay, now how can we come up with such an oracle, or how, like, what can we do so that we can find these basis functions which are suitable for a problem? Any idea? Okay, so there are, okay, the class is more active in Zoom than in person. Okay, so for every question there are many answers. I really appreciate that, but I also want answers. Okay, so people in Zoom, it doesn't mean I'm ignoring your chat. I'm reading all of them, but I also want people in the class to answer. So how would you? There are good answers and questions in chat. Okay, but before that, like, so how, any intuition here in class? Yeah.
We could do some meta learning and already solve the problem to try to fit the best that exists regarding the type of problem.
Okay, well, probably this is a very complex solution, but it is not a bad solution. The solution is to do some sort of meta learning to learn the basics based on a bunch of problems that you have solved so far. Okay, but we can have a simpler solution here. So the simpler solution is just to learn the basis functions, right? Like so. So one of the basic toolkit of this course is like we are trying to learn everything, right? Like so automatically. So we can also learn these basis functions. Okay. Now the good thing is, if we can develop a generic procedure to learn basis functions, then we can take any problem. We can learn the basis function for the problem so that the problem becomes easier, and we can use a simple classifier on the top. Okay. It could be perceptron, it could be logistic regression, or it could be SVM, but we can use this linear classifier on the top of these learned basis functions. Is that clear? There's also a question in chat. So what's the difference between basis functions and feature engineering? They're actually same. So like the idea of coming up with basis function for a task is also sometimes known as feature engineering in the literature. Okay. So pre-neural network, researchers spent a lot of time in feature engineering. Like whenever there is a new task, whenever there's a new machine learning problem, somebody has to develop the data and somebody has to sit and do these features. Like so somebody has to think about, okay, how do I construct basis functions, nonlinear basis functions easily, so that we can actually use simple classifiers that we already know, right? Now, so our goal for today and maybe for the next week is to learn these basis functions in an automatic way. Okay, to do that, we're going to move from equations to graphs because it is easy to explain these things in graphs. But of course, you can go back and change every other algorithm that you have seen to graphical representation as well. Okay. Now, for this XOR problem, right? So a perceptron would look something like this. Like it is going to take x1 and x2 as input. Okay. And it is going to multiply these x1 and x2 by some weight, w1 and w2. Okay. And make a prediction, right? Of course, there's also bias. I'm just removing the bias here. You can add the bias. Okay. Now this is my perceptron unit. This perceptron takes two inputs, x1 and x2. So this is equivalent to w1 x1. So this is basically w transpose of x, right? So you had, I think the basic perceptron was a step function, right? Like f of w transpose x, right? So where f was the step function. So this is the graphical representation for the same perceptron. Okay. Now, if you have basis functions instead of input, then the input to the perceptron is going to be phi1 and phi2 instead of x1 and x2, right? So you're going to give phi1 and phi2 as input multiplied by w1. So this is phi transpose x. Sorry, phi transpose, sorry, w transpose phi of x, right? Now, so what we discussed is the difficulty of learning this, right? Like this is very difficult of finding the good phi1 and phi2, right? Now, instead of finding a good phi1 and phi2 manually, so how about we learn these as well? Okay. So the way in which we are going to learn this is we are going to take the actual input x1 and x2. Okay. I'm going to learn phi1 as a function of x1 and x2. Similarly, phi2 as a function of x1 and x2. Once I have these things, then I can pass this with w1 and w2 to my perceptron. So this is my perceptron. This is my perceptron and this is my basis function. Is that clear? Now I need some parameters here, right? Like so, let's say I have something like v11, v12, v21, v22. Okay. Now my phi is nothing but some f of v transpose x. Or V is a matrix which has v1 and v12, v21, v22. And then I have my final output of the perceptron y, which is some function of w transpose phi. Is that clear? So we have made the setup much more elegant now. Like so, there is no more issue of finding good basis functions. Like, so we're going to learn the basis functions. Of course, we haven't discussed how to learn these parameters, right? Like, so that is the learning problem. But for now, what we have is, given the input, we can learn some basis function representation, and from that we can learn a classifier. Is that clear? Yeah.
Just to be sure, both these functions are
Or
both these functions are different. The one for phi and the one for y.
oh yeah. Okay, maybe I'll just make this G to avoid the confusion. Okay. Now, so this idea of learning basis functions, right? You're kind of learning a representation or transformation for the data, new representation for the data. Okay. So this idea of learning basis functions is also known as representation learning. Is that clear? Okay. So now we are going to generalize this. Okay, then that is neural network. Okay. So how do I generalize this? Like, so you have some input, x1 and x2, and you are learning some basis functions p1 and p2. Now these are functions, right? Like, so v11, v12, v21, v22, right? And then you have w1, and then you have w2, and then you have the final one. Right? So now we are going to call this. This looks like a layered architecture, right? Like, so you have inputs, then the basis functions, then the output. So we're going to call this first layer as the input layer of my neural network. Okay. And we're going to call this as the projection layer, which projects the data to a new basis function space. And this is my classifier, or the output layer. Okay. Now, these V's that you are seeing here, right? So these are projection parameters. And the W's that you are seeing here are classifier parameters. Is that clear? So each of these individual circles that you are seeing, right? Like, so this, like, okay. So we're just going to call them as neurons. Okay. So this idea of neural network was inspired from the biological neuron and the biological neural network that we have in the nervous system, right? Like, so which is basically a bunch of units having connections, right? Like in this case, you have a bunch of input units, they connect to the projection units, and then these projection units connect to the output unit and so on, right? Like, so that's why it's called neural networks, and each unit is called neuron, but we will not get into the biological motivations in this course, okay? Now, what is elegant here is the fact that we're going to learn both the classifier parameters and also projection parameters simultaneously by minimizing the final error function. Is that clear? So we're not going to first find the basis functions and then going to learn a classifier on the top of that. They're going to learn both together, like at the same time. Okay. Now, like what I call as projection layer, right? Like, so this is also called as the hidden layer. Okay, it's called hidden layer because it's kind of hidden in between, and we don't really worry about what the value for this hidden layers. So remember, our goal is not to learn the best basis function. Our goal is to learn the best possible prediction, right? So basis function is just one step in between to help you achieve this prediction. So that's why we are going to call it a hidden layer. Like, so it doesn't matter in the end, like what is there in the intermediate layer. Like what really matters is the final output. Is that clear? Now, this whole architecture, which I called as neural network, okay, so it's also sometimes called as multi-layered perceptron or MLP. Okay, which is to signify that there are many layers, and in the final layer you have a perceptron. But in the final layer, you can really have whatever you want. You don't need to have perceptron. You can have a logistic regression. You can have SVM, like anything that works on the top. Is that clear? Any questions so far? Okay, so probably we will stop here and take a break for 10 minutes and then talk about how to learn these parameters. Okay, we'll stop here.